Okay, it's a couple of minutes past, so I'm going to get started. If anybody else trickles in, we can recap things. I might just come and close these. Oh, you doing the doors? Thank you. Perfect. Okay, so this is going to be a tutorial about GPU deployment, right? And that's like a very kind of nebulous thing to say. The main things we're going to focus on is like setup, installation, software environments, and then looking at some profiling and debugging tools. This is kind of, it's all the bits that are not how to write CUDA kernels, which I've kind of intentionally tried to make it all the stuff around the outside that often trips people up. We put all of this material together for like SciPy and EuroSciPy. So the slot that we had at SciPy was like a 4-hour long tutorial. So there's a lot of material in here. This is going to be like the highlights reel of what's in there. But I kind of, this is a small group, so hopefully we can kind of go through in a way that's tailored and guided by what you're interested in and what you want to explore. Because we could spend a lot of time going through all of this various material. To introduce myself quickly, my name's Jacob. I've worked at NVIDIA for a while now doing Python GPU things. I'm a long-time Dask maintainer and other projects within this community. And I spend a lot of time thinking about how to like install and run different things built with our libraries on various cloud platforms. So people are trying to use various GPU accelerated Python libraries to get stuff done. And a lot of that involves like, well, how do I get a VM on the cloud? How do I get an allocation on an HPC? How do I actually get the GPU? Because, I've got a MacBook Pro here, like there's no NVIDIA GPU in it. Like I need a GPU from somewhere else. So there's a whole bunch of like hurdles and things you need to deal with. So hopefully I can share some of that knowledge with you today. We've also got Camille from NVIDIA as well here. So if you have questions, put your hand up. Hopefully you can walk around and kind of deal with stuff. But again, it's a small group, so hopefully we can kind of deal with a lot of things as a group. There's a couple of things before I dive into like the intro notebooky slidey stuff. There's two things you might want to start doing. So we're going to go and get some GPUs from the cloud. We have an allocation of resource that we can go and use for this tutorial today. So you might want to go and sign up for that and start launching a VM. So in this first Markdown file, it tells you how to go and sign up and how to pick a machine and things. I put the link in the Discord. So there's this big Brev invite link here. This will add you to an organization, right? Brev has this concept of organizations. It's in this current room, so it's the room 119 Shannon, ground floor. But if you've not heard of Brev before, Brev is this platform that we have that basically gives you the ability to launch GPUs on various cloud platforms, whatever you kind of want, but we manage all the driver installation and all the kind of gnarly bits. So you can sign up for Brev. It's a free platform. It has this concept of like organizations. So I'm clicking up here in the top right, where I have my GPU deployment SciPy organization. I'm like a member of a bunch of organizations. When you first sign up to Brev, you'll get some kind of auto-generated organization for you, but use that link in the Discord and it will add you into the organization for here. So make sure you log in and you get it so that it says this GPU deployment SciPy up in the top right-hand corner. And you should see there's some credits in there. We've got like $800 of credits allocated for running this session. Please don't spend it all on one giant VM, but there should be enough to kind of play around. I'll leave you all in the organization for a little while afterwards as well, so feel free to play with stuff, but then we will kind of kick everybody back out. You can go and sign up yourself if you want. But when you come in here, if you go on GPUs at the top and click it, create environment, it gives you a choice of like which NVIDIA GPU would you like on the machine. This is kind of like an NVIDIA first way of doing things. So you think about what hardware you want, and then it tells you like, oh, you can get that on AWS, you can get that on Azure, and you don't need accounts on any of those platforms. Like Brev handles all of that for you and just kind of passes the cost through. So for this session, we're just going to choose something around the $1 an hour kind of price point, just to keep it simple. I started up in L4. So if you come into here and click L4, it gives you like a big list of all the different places we could go and get an L4 from. I chose the top one, which is just a Google Cloud VM, 85 cents an hour. to go and get an L4 GPU. Feel free to kind of pick whatever you want, but I ideally pick the same as me because then you have the same experience as me. But if you want to experiment with other stuff, there are other machines as well on here. But L4s are reasonably, they're modern. They've got 24 gig of VRAM. It's enough to kind of play around and do some bits and pieces. So when you come in here, you choose the VM that you want, choose the provider, give it a little name. I suggest including your initials or your name, because everybody will be able to see everything in this shared org. So just kind of identify it as yourself. All the rest of the defaults totally fine. We can talk about what they are later if you're interested, but it doesn't hugely matter. Just give it a name and click deploy. So if you want to do that while I'm talking, then it will give it a few minutes to boot and do whatever. The other thing you might want to do at the beginning of this session is later on, we're going to do some profiling and have a look at some various profiling tools. And one tool we have is called Nsight Systems as an NVIDIA profiler. And it has this desktop app where you can open the plots and look at the visualizations and things. So we're going to run some profiles on this cloud machine, and then we're going to download the traces, and then you can open them in this viewer. Now, unfortunately, that viewer is half a gigabyte. To download and install this desktop application. If you want to go and do that, you can go to this link, also in the Discord, choose your operating system, download it. Hopefully conference Wi-Fi. It's been quite fast for me this morning, but if we all try and download a half gig file, I don't know how long that will take. So again, you might want to just start that, download it now, so you can install that. Equally, if you don't want to install this, just watch me and I'll show you what it is all about. So if you start doing those things, I'm going to go into this little intro slide deck. Now, as I say, this is part of a big tutorial, and there's a lot of slides in here, and I could probably spend 20 or 30 minutes on the slides, and I don't really want to do that. I want to tinker around and do some stuff. So I'm going to flip through the slides, but if there's anything you're interested in, put your hand up and we can slow down and kind of talk through some of this stuff in a bit more detail. This is also a good opportunity for me to ask you questions about kind of how you're using GPUs, so I can tailor things as we go through. So you're all in this room because you're interested in GPU programming to some extent, which is great. So hopefully you are aware of the reasons why we reach for GPUs in various workloads. But the whole kind of nature of doing parallel programming is a fundamentally different programming paradigm to working on the CPU. And there's all these little gotchas and different things you've kind of got to think about and consider. And so one of the things we really try and focus on in our group, I work on a bunch of libraries that are part of this Rapids umbrella. This is cuDF, cuML, cuOpt, cuVS, whatever. All these libraries are intended to feel natural, feel like they are going to fit within the existing tooling ecosystem, right? So as a Python developer, you can come in, you can pick up one of these things, you can use its API, and it should feel straightforward. It should feel normal. And familiar, because we try and copy the APIs or act as plugins to existing libraries to get that. But we're kind of obscuring a lot of complexity from you in doing that, right? And there's kind of pitfalls to us doing that for you. So just to kind of touch on some of the fundamentals that you might be interested in. Actually, before we do that, who here is currently using GPUs to do things in your work? Okay. Shaky hand. Why shaky hand? Okay, so you're using the one inside the machine. Yeah, okay. So I mean, I guess in that case, you're still in this paradigm where you're running code and it's reaching out to some accelerator through some binding, and there's some abstraction there, right? So, okay. Well, let's talk about this a little bit then. So the reason that we go to GPUs for things, because the hardware architecture is fundamentally different to a CPU, right? In a CPU, you tend to have a small number of very large cores. They've got a lot of cache. They can kind of think about these sequential operations. They can do one thing at a time. Whereas the GPU has got many, many, many cores and a big shared cache and a big chunk of its own RAM. And instead of each one of these cores doing a different thing in the way that you would think about your laptop, you might have a bunch of different applications running. You might have a different load of processes running. Your operating system is handling, swapping all around between all of those and kind of sharing those small number of cores between all those processes. When it comes to GPU programming, we tend to think of it as a large chunk of resource where we are writing parallel algorithms. And so I'm going to run one application at a time on my GPU, but that application is going to use all of the cores. And so we can kind of restructure the way that we handle things like cache because of this different way of writing this code. And so you can write these really high throughput applications that really leverage all of those cores, but it's like a fundamentally different programming paradigm. Yeah, I just said all that. One of the things that we tend to struggle with, I think, initially when you start looking at GPU computation is thinking about kind of what is this device? You often talk about a GPU as a device. It's a thing that is like plugged in inside my computer or this computer in the cloud. It's like a separate machine. It's a separate piece of hardware. And it can be quite opaque to think about like, well, how does stuff get to it? How does it run stuff? How does it do things? And so like my mental model that I prefer is to just think about it like it is another separate machine, right? If I want to take some code from my laptop and run it on a VM in the cloud, I have to get my code from my laptop to the VM in the cloud. I have to get my data into the VM in the cloud somehow. And then I have to actually like log in and run Python my script, right? So you've got all these kind of things you need to do to copy data, to access data from other places, to execute commands, all these kind of things that you would do on a remote machine. You have to do all the same stuff for the GPU. So you have to copy all the data from the main memory into the GPU memory. You have to launch CUDA kernels, right? Which is basically where we're saying, I'm going to call a function on the GPU, but just think of it like running a Python script on a remote machine, right? You're kind of executing something remotely, and then you need to gather those results and pull them back to where you are. And these are kind of the bottlenecks in using GPUs, right? Moving that data from your machine to the device itself is kind of slow compared to the amount of computation that the device can do. So you need to be kind of thoughtful about how data is moving back and forth. And there is also some cost to saying, I want to call this function on this GPU, right? We call it like launching a kernel, but like there's some small amount of cost in terms of launching a kernel. And I would think about it in terms of like, there is some cost to starting the Python interpreter. If you have an application that calls subprocess and like subprocessed a bunch of other Python interpreters, there's some overhead, there's some startup cost to that, right? And you can, if you have very, very small functions you're running on the GPU and you're calling lots of them, like you can spend a lot of time just negotiating calling the function rather than actually doing what's inside the function. I'm not going to dig too much into actually how GPUs do processing unless anybody's super desperate to hear about it. But like the main way to think about it is that it can do vectorized operations in a way that the CPU can't do. Right? And I think as a lot of people in this community have probably gone through that transition where you learn NumPy and you start thinking about like, oh, I'm going from Python and for loops to calling like a NumPy vectorized call. Like that mental step that you have to take is kind of the same mental step that you have to take into GPUs. And you just think, okay, I'm going to make this call and it's going to do some vectorized operation using all of this kind of cores in the hardware. So you have these kind of parallel do's that you do on the GPU. Let's not talk about GPU hardware at that level. The places where GPUs are super important are when you're compute bound, right? As we said, calling code on the GPU and moving data to the GPU is the expensive part of using the GPU. So if you're doing some kind of IO bound operation, you're going to spend all your time still in IO and you're not going to get much benefit from this. I come from like the weather and climate world where you're running these huge simulations, you're getting these huge data sets, and the kind of operations you're doing on your data isn't, I mean, you can do all sorts of stuff with weather and climate, but a lot of things that I find folks in that world struggle with is just like, I want to take a mean of a 20 terabyte data set, right? Or I want to collapse across this dimension using min or max, or like some kind of trivial compute operation. And the problem is just moving that data around. And so like GPUs are not going to help you in that world. Like if you move the data, of course, a mean on a GPU is much faster than a mean on a CPU. But if you're going to spend all your time trying to stream this like 20 terabytes of climate data through, like that's still where you're going to spend your time. Whereas if actually what you want to do is go over that grid of weather data and do kind of semantic analysis, I want to do some kind of machine vision thing on it. I want to see a storm. Is there a storm in this picture? I want to run some kind of model that is running a convolution or something over my data to decide whether there is a storm or not in there, that's way more computationally heavy. And so you're going to like swap in a chunk of weather or climate data. You're going to run this kind of compute heavy operation. The GPU is going to do that very, very well. And then the data coming out of that will be like, yes, storm, no storm, right? Like you binary Boolean data coming in and out. So you'll likely have heard of CUDA, right? This is our kind of compute world within GPUs. And it's easy to think of CUDA as like this, right? And often Python people see this and it's like, I don't want to really do this. This is like, you know, this is C++ and I don't want to write that. And we're not going to. That's hopefully all the C++ you're going to see in this tutorial. But I kind of just want to communicate that like CUDA is more than just the programming language extension in C++, right? So you can write, of course, CUDA C++, you can compile it and it runs on the GPU. But CUDA also kind of contains all of the logic around how do I copy the data in? How do I copy the data back out? How do I actually call the function? It's kind of got all the plumbing and pipework around actually using the device as well. So when we talk about CUDA a lot in this tutorial, we're going to be talking about the plumbing rather than the actual like programming language extensions. So within the kind of CUDA ecosystem, we have this plumbing, we have this programming language. And then on top of that, like in kind of any other programming, we have libraries, right? We have standard libraries, and then we have all these kind of specialized libraries that have been built on top of CUDA over time. And so, you know, you have all the compilers and all that kind of stuff. But then like a level but above that, you have all the kind of math libraries, you have your normal BLAS libraries and FFTs and whatever it is you want to do. There are libraries for doing communication between devices. So if you have more than one GPU, you need to think about how data might be copied or read between them. So you have some kind of communication library. There's like a whole bunch of like low-level libraries that we have that just kind of make all of this world work. And we refer to this generally as the CUDA toolkit, right? So this, you can think of this as just like a collection of standard libraries that you get from NVIDIA that does stuff. And almost anything you're going to do that uses GPUs will depend on one or more of these libraries in the CUDA toolkit. But not necessarily all of them, right? Whatever application you're using will have its dependencies, and it will just import those and use those and compile with those libraries. But I think historically, we've thought of CUDA toolkit as like a thing. You install CUDA toolkit, all of the libraries, and then you just depend on the ones that you need. And I think this is kind of a hangover from compiled code world. Whereas maybe in Python world, actually, you're like, well, I just want to depend on the libraries I want to depend on. That's part of my application. I want to put those in my pyproject.toml, and I want to just depend on those. And we'll kind of dig into that a little bit in a bit. But then above that, when you actually want to write some code that uses these libraries, that uses this like low CUDA plumbing, there's a few different options. There's a few places where you can come and do this in Python, right? You can come and just use high-level libraries that we have. You can use CuPy, you can use QDF, you can use these libraries that kind of fit into our existing world, right? CuPy follows the same API as NumPy. QDF follows the same API as Pandas. QML follows the same API as scikit-learn. You get the idea. We have these kind of high-level libraries. You can swap them in, you can use them. It abstracts absolutely everything away from you. You also have the choice of using writing Python code that then gets compiled into like low-level code that runs on the GPU at runtime. The most kind of popular library for doing this is Number. You can write Number kernels in pure Python, and they'll get compiled by the toolchain as you run them. Also, if like PyTorch has like a whole bunch of JIT compilation stuff in it as well, you can do all sorts of fun things where you're working at this Python level, you're writing functions, and they'll get compiled for you by whatever tool it is you're using. And then we also have these other libraries, like CUDA.core, CUDA.bindings. These are these kind of plumbing pieces that I mentioned, right? These are kind of our Python entry point into those. So you can import CUDA and then call methods and things to interact with the hardware itself. These are kind of like low-level control things, and we'll do a little bit with that. And then kind of above all of this, we have what we roughly talk about as rapids and CUDA-X, right? So these are like the very high level building blocks of, you know, I'm trying to do data science, I'm trying to do climate science, like what libraries do I need in that space? What actual like very specific operations am I going to have? So, you know, we have scikit-learn and NumPy and NetworkX and all these kind of things. We have cuOpt for doing optimization problems. We have QVS for doing vector search, which, you know, is super popular at the moment. And you'll find there's thousands and thousands of kind of functions that have been written for you, right? Everything on the GPU is called a kernel just because of history, but like if you just think of this as there's these huge collections of functions that have been written for you. They're either written in C++ and they have bindings into Python, or they're written in Python and they use this just-in-time compilation. But from a Python developer level, you just call those functions and they use the hardware. And so you roughly have this stack. And hopefully from these slides, if you take anything away from it, this stack is kind of the most useful piece, I think, in that you think you have this hardware at the bottom, you have this physical device. On top of that, you have a driver that just lets the operating system talk to that device. And then above that, we have a few different layers of libraries that go through these different abstractions. You have your low-level toolkit libraries. Think of this like the C standard library or something. You've got CUDA Python and all these kind of plumbing layers that are binding you into the toolkit from Python. And then you have these high-level libraries within Rapids and CUDA-X. And then above that, you have your Jupyter notebook with the thing you're trying to get done in it. And you're kind of using, through that stack, you can use anywhere in the stack if you want, but a lot of folks are kind of interfacing down through this in this kind of top-down way. So I guess one of the intents of this talk is to talk about software, but also to talk about software environments, but also to talk about performance. So I think a key thing to think about is when you're doing stuff on the GPU, you really don't want to move data back and forth. If you can leave stuff on the GPU, leave stuff on the GPU. And I think if you go to any kind of tutorial or workshop or anything that talks about these kind of stuff, you'll hear that people say exactly what I'm saying, right? Run your code on your GPU, do very vectorized operations, make sure you're not copying data back and forth. But I think there's a lot of an expectation for you to look at the code and know when you're doing that. Do you know what I mean? Like teaching you, explaining to you what bad practice is. You don't often see actually teaching you how to measure whether or not those bad things are happening. And so this is kind of what I want to focus on in the rest of the tutorial. So let's go and get a GPU and do some things. Who here has managed to get a Brev instance and get things up and running? Nearly everyone. Does anybody need any help with the Brev step of stuff? Oh, go on, mate. Oh, that's a shame. So if I go into my VM, was it this link that you clicked? Yeah. And then, oh yeah, it makes me.
I can see this one, but then it doesn't open the notebook for me. I get a 400 found page.
Yeah. You don't get this file?
I don't get this one. But
okay.
It's a link. I just click the link and it says this Jupyter something Brev lab.
Yeah. It's possible that the VM died during startup.
But it says healthy.
Yeah, it might do. I feel like for the sake of this tutorial, it might be better to just delete it and create another one.
Okay.
It may have just been a transient error. I have seen this kind of thing before. If it still doesn't do it the second time, we'll come and really dig in and help.
If you use a name, I can use the same name. Does the name mean anything?
No, I mean, they're unique in that you have to delete it, and then that takes some amount of time, and then you can create one with a new name. But I maybe use just a variation.
Yeah.
Okay, so hopefully everybody else can get to this point where you have Jupyter open, and you can kind of poke around. Now, let me go back to the setup, right? So we run through all these things. Now, you're more than welcome to do stuff in Jupyter. I think everything we're going to run through in the tutorial, you can do in Jupyter, you can do it in notebooks, you can do it in the terminal in there. You may also want to do things from your own command line on your own machine, because these are just VMs in the cloud. So just to show you a little bit of how we do that, there is a Brev command line tool that you can install. I think those instructions are in there, how you go and install that on whatever machine you're on. You run Brev login, and that will kind of kick you to the browser and get you to authenticate and then bring you back. And then you should be able to do this brev ls command, right? Brev ls. And for me, it should just list my machine that I started and show me the statuses. These are the same statuses that you'll see in the dashboard, but you can also see them in the command line. Now we can do something like, I could do brev shell and then the name of this machine. And this basically under the hood does SSH, right? It figures out how to get from you to the machine in the cloud, wherever that is, and firewalls and magic and whatever. And it will kind of connect you through. This is a very kind of straightforward way of getting in. It takes a little while to just think about what it's doing. Sometimes it has to do some funny proxy jumping stuff, but it'll get you in there, right? And you can get into that machine. So from here, I could run like NVIDIA SMI. Let me make it a bit smaller so that doesn't do that. I can run NVIDIA SMI, which is our kind of our hello world of like, I have a machine and I have a GPU, is everything okay? We run NVIDIA SMI, it gives you a dump of kind of the state of the device. If NVIDIA SMI fails, like you probably have a driver issue or something is like misconfigured at the like very low level of the machine. But Brev has set all this up for us here. But just to show you like another way of doing this same connection thing, because it's how I prefer to do stuff. Like Brev shell is the one you'll see in the documentation, but you can also do Brev refresh, and this does the same. It figures out the same connection route from your machine to that machine, but it updates your .ssh/config file in your home directory with an entry for all the machines that you have available. So you can just SSH directly. So if I now do my brev ls after I've refreshed my thing, my machine is called J. Tomlinson Teacher. If I just do SSH that machine, it just SSHs in, right? And like I prefer this because I can also then do SCP and rsync and copy data back and forth and copy files back and forth, and it's a little bit more normal, right? Than using brev shell. But there's a lot of like convenient stuff in the brev command line tool, and it's super awesome. But like I also just like being able to SCP stuff. And if I want to do like port forwarding, I can use SSH to do port forwarding and things. But I'm going to stay SSH into this machine as we run through. But you should all be able to get to this kind of same place, whether you want to do it, you know, open your terminal in your notebook and run NVIDIA SMI to make sure things are alive, or whether you want to SSH in and run NVIDIA SMI. If you can type in NVIDIA SMI, that'll get you to that same point. Okay, good. I like the title of this page in that it's like we have a GPU, now what? So the next thing we need is some software, and there's, as I said, this whole stack of stuff. Now, one of the reasons why we chose Brev and the bare minimum install and not telling you to do anything else is to kind of show you the from the ground up, how do we get all the bits of this stack and where do they come from? Because in this, in the kind of basics setup you get from Brev, you get the driver because NVIDIA SMI works. We have the driver, we can talk to it, but we don't have anything else. If you chose a cloud provider that's not Google Cloud in that drop down, you may have got different things. I know some of them are a bit more, they add more stuff, but Google don't give you anything out of the box. So we have to install some packages into this machine. Now we're going to start doing this in like the Python way, because this is a Python conference, and it's kind of nice that you can get basically everything the Python way now, but there's a few different ways of doing things. So who here is like a pip UV kind of person? Okay, and then who is like a Conda Pixie kind of person? Okay, good. Conda or Pixie? Conda? Pixie? Okay, a mix. We did the same thing at SciPy. There were no hands for Conda. Super interesting. Like everybody seems to be in Pixie now. Okay, the way that we've written this is it has instructions for all of them. My plan was to go with whoever put the most hands up, and we'll do that one, and everybody else can follow along. There was such a mush of hands, I don't really know which one to choose. What I might do, I'm gonna go down the UV road, partly just because UV and pip, as you probably know, is the worst experience of all of these package managers, and has more gotchas and more caveats and more problems. And so let's go down that road because it's the slightly harder road. If you want to follow along, if you are a Conda or a Pixie person, feel free to like just scroll down and find those sections in here. So if you want to do Conda, just scroll down to the Conda bit, or if you want to do Pixie, keep going to the Pixie bit. We have the environment files for all of those. There's probably just going to be like extra steps for UV and pipwell just because of the limitations of those tools. But let's, yeah, okay, I'm going to do the UV pip road. I'm going to make that decision. So one One of the reasons that, like, I guess Conda and Pixie exist is because historically it was hard to package compiled libraries, right? And so Conda packages were created to solve some of that. And we have for a long time packaged all of the CUDA toolkit as Conda packages. They're on Conda Forge. You can install them with Conda or Pixie. In pip world, it's a lot harder for us to it's a lot harder for us to put the same software into wheels, just because wheels are a little bit more limited compared to Conda packages. There are some challenges in how we can link stuff and connect things together. Things are getting a lot better. We do provide wheels for a lot of stuff, and I will install those from PyPI in a minute, and you'll kind of see all of that going on. And like, there's a whole thing going on in the Python community that's part of this like Wheel Next project to improve wheels and kind of close that gap a little bit. And we'll get there and everything will be wonderful. But in the meantime, we're kind of in this slightly messy situation. One of which is a lot of packages that you'll find in the pip world don't know where to get CUDA Toolkit from at all. And they just kind of look on the machine and be like, where is CUDA Toolkit? And they're basically going to do something like this like ls command. So if I have a look, user local CUDA is where, if you like apt install CUDA Toolkit, this is where it'll end up. Right? You use the system package manager, and you're going to pull in all of CUDA Toolkit. It's quite a big lump of loads of libraries, and they'll get put into user local CUDA. And you'll find on this machine, if you start one of the GCP ones, that it won't be there because we haven't got the system packages installed. So we should have UV already out of the box on this machine. Yeah. Let me just check where we're going with this. So I guess my point of showing you that we don't have anything in user local CUDA is we're going to try and get everything from PyPI in these examples. There are a few libraries that you might run into issues. If you're using CuPy older than like a few months ago, it will be looking for these system libraries. It won't know how to get it from PyPI. If you're using like Torch or QDF or anything kind of more modern and recent, they will be able to use the wheel packaged versions of these from PyPI. But you may, there's kind of these packages have a bit of a reputation for being very large. And this is just some of the limitations of wheels. Like when we build one of our CUDA toolkit libraries into a wheel, it has to have all of its dependencies in with it. And then if you install another CUDA toolkit package, that has to have all of the same like C++ dependencies with it. You can't do the dynamic linking between them. So you end up with some very big packages. So when we do some installs, we're going to get some of those. Again, wheel next, hopefully things get better, it'll all be good. The other caveat that you'll see when we install things is we have on PyPI, this is a limitation of PyPI, it has no understanding of the GPU or the software stack or anything about that, right? It's a Python-focused package manager. And we have different versions of CUDA, right? CUDA 11, CUDA 12, CUDA 13. And we need to install the right versions of the libraries for the right version of CUDA. Think of it like we have to install the right packages for our operating system or the right packages for our libc that we have, right? Now, Conda and Pixie are aware of CUDA, right? They have this idea of virtual packages. They can go and use NVIDIA SMI. They can figure out what the CUDA version is, and the resolver can resolve the right package. So you can just do Conda install CuPy, and it will work. It will figure out the right version of CuPy for you. But you can't do pip install CuPy or pip install UV pip install CuPy because those tools are not aware of kind of the other dimensions of the resolve that it needs to do. So we instead include that in the package name. And so you'll see some package names in here like CuPy-CUDA12. And that's because we're having to put that metadata into the package name because we can't pass it any other way. And again, wheel next should be fine. If you're going down the Conda road, you won't see those suffixes on the packages.
Sorry, does it mean that you're bundling the whole CUDA runtime in each package independently?
We're bundling. So when you install CuPy, it will pull in CuPy and it will depend on one of the CUDA toolkit or one or more of the CUDA toolkit packages. Those will also get pulled in as Python dependencies. They are packaged as wheels and they're in PyPI. And those will depend on the CUDA runtime. And depending on how things are, that will get, the runtime itself will get pulled in as a package as well. And so there are kind of some shared level dependencies in that kind of tree. But yeah, this is why they end up big, because there is duplication between which components of the CUDA toolkit get bundled in each wheel.
I guess if you install Torch together, you
it's tricky. It's partly because the Rapids community choose kind of the LTS supported releases of CUDA to build against, and we built, there are like blessed releases of CUDA that we focus on, and the PyTorch community do whatever they want, and they often choose different ones that are not the LTS releases, and so we end up in sometimes these weird situations where they've built against one CUDA version and we've built against another CUDA version, and things are incompatible and there's just gaps and stuff. But again, things are getting better, but you know, we've got more PyTorch people at NVIDIA now and stuff as well, so all that is kind of working.
Can you use a microphone?
Yeah, it's all right. I can hear myself, so I didn't know if I'd pointed it at myself well enough, but I can, yeah, I can use the microphone. Okay, so one thing that you'll find on this Brev machine, and this is something that is specific to Brev, is if I do ls.env, .venv, I missed the V. There is a virtual environment already here that's been created by Brev when this machine started. And this is how Jupyter exists, right? The fact that you can click in the UI to open Jupyter, right? When this machine booted up, Brev ran like a post setup script that just did like UV create, you know, UV venv and then UV pip install Jupyter. And it started that as a service. So there's this little existing Python environment hanging around. And we're just going to reuse that so that we can do some stuff here. If you're doing the Condor and Pixie path, like create your own separate environments, that's totally fine. But I'm just gonna source activate this Python environment we already have. And if I do which Python, we have this Python that exists here. So this is not the system Python, this is the one that came from Brev. If you're doing this on any other machine that's not Brev, just use UV, create a new environment, and go from there. And I'm just gonna do this, oh yeah, the other thing we need to do is clone the repo. So I put the link to this repo in the Discord, but this has got like a bunch of scripts and stuff in here. So I would just git clone that git repo and cd into there. I'm gonna install, we have these environments. Let me open it in Jupyter so you can see what I'm talking about. GPU deployment tutorial, EMS. We have these different environments. So there's a pyproject.toml in there that I'm gonna use that just has like a bunch of dependencies that are used through this tutorial. But you can kind of see like, well, let me make it bigger. You can see here, we're installing QDF, CUDA 13, QML, CUDA 13. Like we've had to specify their versions, QPy, CUDA 13X. You can see each package doesn't have any consistency on these suffixes either. And you'll notice in this, we are pinning to some pre-releases. This is another, we wanted to show you some stuff that we fixed in the latest release. It's not released yet. UV and pips -- pre flag is broken in various ways that causes other problems and other headaches. So we can't actually install these with -- pre because then it tries to bring in pre of almost everything it can find and things get messy. So I've hard pinned to some pre-releases here and added this this other upstream thing. Don't worry too much about it. As of like in a couple of weeks, you can just install the normal versions. We've done the same in the pixie.toml and the Condor environment, right? They're just using this nightly channel and they've got the same pins in there. So it's the same concept, right? Pulling from nightly, pinning to these pre-releases. But all these environments are equivalent, right? They're just pulling in these new versions. I think you'll also find with the Condor and the Pixie ones, because you're creating them fresh and we're just specifying Python greater than 3.11, you'll get 3.14, whereas the Brev one, for some reason, has given us 3.12. But it shouldn't be a problem. So what I'm gonna do, I've activated this environment and I'm just gonna install everything from this pyproject.toml. So I'm just gonna copy that command. Oh no, let me cd into cd env, and run this. And UV is going to pull these in. And you'll see some of these are quite large. It's pulling in big chunks of the CUDA toolkit as it goes through. Hopefully we'll see some more output. Okay, so you can, it's very fast. There's a whole lot of stuff coming in. There's a lot of NVIDIA packages, right? NVIDIA QSparse, NVIDIA QFFT. These are the CUDA toolkit libraries that we've packaged up and put on PyPI. So these are coming in through your Python package manager. You don't have to worry about installing these with apt anymore, which is nice. But as I say, these are kind of large. So this is like a multi-gig install to like install a few libraries. But we're constantly shaving down the size of these wheels, so we'll get there. And the one thing that was contained in that little environment file is there's a library here called Jupyter MV Dashboard. This is a plugin for Jupyter that gives you some visibility into the GPU. So we've included that in this. That's been installed into the Jupyter that my Brev machine started for me, but I do need to just quickly restart that service for it to load the plugin. So if I just do sudo system control restart Jupyter, and then I should be able to refresh this page. And over on this left-hand side, there's a new little icon that looks like a tiny GPU. And if you click that, there's some dashboards that you can open up. So you can open up like GPU memory, GPU utilization. These are like task manager style plots, right? They show you what the GPU is doing as we do stuff. I'm also just going to open a quick notebook so we can just kind of poke it and make it do something so you can see it doing something. So if I want to type and I want to put that, I'm going to go like that. We'll see if that works. Okay, if I import CuPy, we should get CuPy. And let's just make an array for a second. Okay, it's NumPy API, I'm just doing it with CuPy. You can see I allocated a bit of memory. Actually, let's make this a bit bigger. No, even bigger. There we go. Right, I'm allocating a bit of memory. Even bigger? Yeah, okay. Right, I've got a 10 gig CuPy array now on my machine, and you can see in these plots, it's showing me like, oh, I'm using up this much memory, and I'm utilizing the GPU. You might have seen it flicker and doing stuff as it populated it with those random numbers. And now, if I want to do something like, for I in range 1,000, x equals x times 2 or something, right? We can, I ran out of memory. Let's make this a bit smaller. So this was that little GPU icon on the side here. After we installed the plugin and restarted Jupyter, this should appear. And then you can open these plots and see what they're doing. But yeah, so if I run this cell, you see the utilization doing stuff. Right, and this is like the first debugging tool that you'll kind of find as you're using some of these libraries and they claim that they're going to GPU accelerate whatever it is you're doing. Like run the code in your notebook, look at the plot, see if it actually utilizes the GPU, see how well it's utilizing the GPU to get some idea of kind of what's going on. You can see the memory usage here. Go on.
Is there a way to get it without Jupyter interface?
So yeah, you have to use the command line, and we'll come on to those tools in a minute. But there are command line kind of equivalents of these. But we built these ones just to integrate. I mean, one thing you'll notice, right, is I was playing around with the sizes of this array. I kept assigning some arrays to X. I made one that was too big and I ran out of memory, and I made a smaller one and ran on that to show you that. I'm still using 18 gig of RAM, right? Because my notebook has caught a little reference to that old array that I made, and it's kind of dead. So again, this is a good way, if you keep running into out of memory issues or something, you can come in and be like, why am I using 18 gig of RAM? This array is not big enough to use 18 gig of RAM, right? So if I restart my kernel, that memory usage will go away. So these are like the great kind of first touch tools to see what's going on. Let me see where I'm at. Yeah, so the rest of this is just kind of that. This is a QDF example of the same thing that I just showed you. I just got excited and wrote it by hand. So that's kind of the end of that one. We should all now be in a situation where you have a Python software environment on this machine. It has some CUDA libraries installed, and we can start playing around with what we're going to do with those. Now, there's 2 more notebooks in here, and for the interest of time, we're like halfway through this tutorial slot already. And so I don't think we'll be able to go into them in like a huge amount of detail, but I'm going to gloss over them. You've got the material. Feel free to like go in and learn more and play with these. But I want to show you this one kind of quickly. This is a tool we built relatively recently. This is called Rapids Doctor. I don't know if it will always be called Rapids Doctor, but we've been trying to build some kind of tool that helps you analyze the health of your software environment. Because it's very easy to get to this point and you're like, okay, I've got a driver, I've got a GPU, I've got a driver, I've got some CUDA toolkit packages, I've got some higher level CUDA X packages like QDF and things. I think everything's okay. I think I installed all the stuff. Brev gave me some things. I don't really know what it gave me. UV gave me some things. I don't really know what it gave me. Like, you can end up in a state where you're here and you think you're okay, but you want some reassurance that you're actually okay, right? And that you've installed some stuff. And so one of the things we installed in this bundle of things is this package called Rapids Doctor, the Rapids command line. But if I run Rapids Doctor, it basically goes through and does like a bunch of health checks, right? It looks at, can I talk to the driver? Can I talk to, like, see how much memory I've got? Can I import some stuff? Is Python okay? Like, it goes through and just does a bunch of smoke tests. Out of the box, the Rapid CLI has a bunch of these tests, and it does them as you install other libraries, QDF, QML, whatever. They can bring in their own tests, and it uses Python entry points for discoverability. So this tool will run specific tests to those. So I've installed QML. I think if I do rapids doctor -- verbose, it will show me what it's actually running and found, right? So it's got like some QML specific checks that it's run through there. So it's done like, can I import QML? Can I call a CUDA kernel using QML? Can I use the scikit-learn accelerator plugin? And there's just like a few little tests. Think of this like PyTest, but it's just trying to like give you some reassurance. And it comes through. It might give you some warnings. So for a lot of situations, we recommend that you have at least twice the system memory to GPU memory ratio, just because you're going to be swapping stuff in and out, and you want to have, if you're going to copy something in and copy it back, you need at least twice that space, right, to get your input and output. And the Brev VM I chose does not have that ratio, so it gave me a warning and said like, oh, we recommend a 2:1. These are just kind of, you know, warnings. They're just a recommendation. But it will also, if something is bad and broken, it will give you errors here. And the idea is that this will always give you like an actionable error. So it'll give you a link to some documentation that will help you resolve whatever that error is. So it's good to know about Rapids Doctor. We also have this other command in there called Rapids Debug. And if you run Rapids Debug, it just prints like a full dump of stuff, like lots of knowledge about this machine. So it calls NVIDIA SMI. It has a look to see like what Linux kernel you've got. It looks at what driver version you have and Python versions. It dumps out, you know, pip freeze, has a look at all the stuff in there. It has a look to see if you've got Conda, other tools. It finds versions of your compiler toolchain, all these kind of things. And this is much more helpful to us than it is to you. But if you're ever working on any of these libraries and you want to go and raise an issue and report something to PyTorch or to one of the Rapids libraries or whatever, like run Rapids Debug and give them the dump of your environment, because that will help us kind of come in and troubleshoot and triage. But it'll also kind of help you kind of come in and see like, oh, I would expect there to be Pixie. Why have I not got Pixie? You know, and it can give you some signal. There's also a -- JSON flag if you want like a machine readable version of the same thing. Again, probably more useful to us than you, but I wanted to show you that tool because it's kind of fun. Now the next notebook in here, actually, before I move on to the next notebook, does anybody have any questions or anything anything to do with like the machine setup, software environment setup, or anything that we've got to this point? Okay, good, cool. Right, the next kind of notebook in here is going through actually using some of these libraries, and I'm not gonna spend time on this because I want to spend the rest of the time in the next notebook and then kind of going off into whatever you want to talk about from there. But the intent of this is to show that like there's a bunch of libraries out there, like QDF, QML, especially, that are intended to be these like zero code change drop-ins for existing libraries. So if you use pandas, great, install QDF onto your GPU machine, load the plugin, and then just keep using pandas, right? And there's like loads of documentation that can show you how to do that. But it will just give you an accelerated version of pandas. Pandas will be swapped out under the hood. It will be using GPU function calls instead of CPU function calls. Hopefully things will be going faster. QML makes the same claim with scikit-learn, and we have like an XQgraph plugin for NetworkX, and like there's a whole bunch of these floating around, and they all make this promise, right? That like you load the plugin and the performance will either be the same or better. If it can't do something on the GPU, it will fall back to the CPU. Same, like roughly, right? There might be a little bit of overhead of like, oh, I tried this function, it failed, I'm going to call this other function. But it will fall back in there. But you can make these tools tell you more information about what's going on. So if I just quickly, I am going to run one of these things, actually. If I just come back up into here, let's just download this little data set. And we have this notebook that just runs a little pandas workflow. But I want to show you this this command here, right? So this is Python -m cuDF.pandas, right? This is how, if you want to do if you have a pandas Python script and you want to run it with the accelerator, instead of doing Python my script, you do Python -m cuDF pandas my script, and that injects the plugin into pandas when it starts up. And then there's this other little flag I've added here called -- line profile. So
What is fine, but this script with pandas is not linked from the slides to post it online.
it's the repo. So I think that one of the steps in the environment setup was to clone the repo, to clone this repo, right? And all the scripts and everything are in there.
I have now a setup because now I have fixed installed. I have environment, but when I open the notebook, it opens with the style clone. It doesn't have my environment activated. How can I activate this environment inside?
Oh, you might need the IPy kernel. You might need to register it. Yeah, but you might need to register it, right? With the.
Yeah, we have to put around the kernel user environment.
Yeah.
Before I start opening the notebook.
Yeah, it might be easier to do this in the command line for now. Yeah, no, I don't know. Or use UV. But no, I'm gonna put that in my notes actually, because we should add that to this. Okay. Okay, so this script, I'm running the accelerator, I'm running dash. Well, let's run it without first, right? If I just run the script, this is just a normal Python script. We can have a look at what's in it if we're kind of interested. Scripts, pandas workflow. All right, this is just opening a Parquet file and doing some group by operations in pandas. It's not, it's kind of bread and butter panda stuff. I run this and it prints out some results and some timings. And that's, that's great and that's useful. But if this is not performing how you would expect it to be performing, and you're kind of wondering what is going on? I've used this magical accelerator, but I don't know what's happened. One of the first things you can do is use this -- line profile, which is a feature of the accelerator. I might need to make this a bit smaller. But this goes through and it runs the same code, but then it prints out the code and gives you a whole bunch of information about how that code was executed. Okay, so this is that same script that I just showed you, but down this side, it's got a GPU time and a CPU time column. And so for every time we call a function, it's measuring how long was spent in each of those functions. And if there was a situation where it couldn't run on the GPU, either because it ran out of memory or that function just hadn't been implemented or something, it would show a number in the CPU time column instead of the GPU time column. Or additionally, right? If it tried doing the GPU one and then it ran out of memory and failed and it tried to do it on the CPU instead, you'd see both numbers in there. But you can kind of see a list of okay, when we called this function, it took this long, and this function took this long. And you can kind of get better idea of where the time is being spent within your code. So as a first look into a basic Python script that you've written with pandas, this is a good place to start profiling. I saw a hand over there.
Who's giving you this flag? Is UDF or pandas?
Yeah, this is part of cuDF. QML has the same flag as well.
But what's happening behind the scenes in the case? The script references in QDF. This is importing lists in QDF and pandas.
Yeah, exactly. So when you do that Python -m cuDF.pandas, it loads that module. That module hijacks the import system and then runs the script. And whenever the script calls import pandas, it just gives it a little shim instead. And that shim decides whether or not it's going to call pandas or if it's going to call cuDF. And it handles moving the memory back and forth between the two. You can do the same.
Did somebody package these outside of Rapids?
No, this is what we do in Rapids, right? Is building these things. We also there's a bunch of ways of doing this. I've shown you the command line way. I don't know if this page will be the one. So there's also, like, if you're doing it in a notebook, you can use this. Let me make that bigger. You can use this notebook magic to just say like load extension qdf.pandas at the top of your notebook, and then it does the same thing, which is arguably not quite zero code change because you do have to modify one cell in your notebook to load the plugin. We've added to the, is it working in here? We did add a little, oh yeah, okay. With this GPU plugin that we installed, it has given us a little drop down here as well, where you can turn on these accelerators. So if I click the qdf.pandas one, that made a quick little call to the kernel and restarted it. That's injected that same thing, right? But there's like a bunch of ways of doing this. We did that for Anaconda Cloud because they were kind of like, you can't say it's zero code change if you need to edit the notebook. Like I want to be able to just open a notebook and run it with pandas and run it with QDF just by a little drop down. So
What did you need to install?
this was the GPU plugin that we installed that gave us this dashboard. It also gave us this button. This is the Jupyter Lab MV dashboard plugin. You, in the instructions, even for Pixie, you still have to install the plugin with UV into the base environment. Yeah, and the interactive manager doesn't work. You got to do it with the command line. There should be instructions for it all, but let me know if you get stuck. But yeah, okay. Like if you want to keep going through more of these accelerators, like there's a bunch of stuff in here. It shows you these line profiles. These are things that have been implemented in those few packages that we've done. And I recommend you go and look at it, but I'm not going to spend any more time on it now because there are loads of different packages you could use, right? We've implemented that for 2 or 3 packages, but there's also PyTorch and CuPy and a million other things that you're not going to have those kind of nice to use tools. So let's dig into more kind of monitoring and debugging stuff that kind of broadly applies to just like Python and GPUs and how we can look at what's going on. So let me come out of this and clean that up a little bit. Yeah, as we saw, right, let's have a look a little bit more at NVIDIA SMI, because this is like our first pass really of having a look at like what's going on this machine. All right, so just to kind of show you, maybe if I wiggle my mouse, it's easier. So NVIDIA SMI, it shows you your driver version that you have installed. It also shows you the CUDA version that you have installed. Now this is, within that stack, this is showing you the CUDA version like right down at the driver level, right? So this is the kind of the lib CUDA C library, basically, that's being linked from all these other things. You can install newer versions of CUDA toolkit libraries because they'll be backwards compatible with this. So this is kind of showing you the floor of what CUDA libraries you can run. But for instance, you might, because we've got 13.2 here, if you try and use like a 13.0 package, you might run into some issues. There might be missing features. If you use a 13.5, which doesn't exist yet, but when it does exist, if you use that, you'll be fine because of the backwards compatibility. If you try to use 14, it won't work because we do major version breakages. So this is kind of showing you your CUDA version floor. And then it has a list of GPUs. So we have only one on these machines that we chose, and it shows you kind of stuff about power usage and things and temperatures, but it shows you how much memory is being used. So I've got nothing loaded at the moment, show me 0 meg out of 24 gig. And it shows us the GPU utilization. And then it gives us a list of processes that are doing stuff. So in here, when I was doing this CuPy example with my notebook, I was looking at the dashboard and seeing I've got some memory allocated and I'm looking at my utilization. We could achieve the same thing just by doing like watch NVIDIA SMI to a certain extent, right? And we can see like how much memory is being used and how much utilization there is. If I just run this little cell again, we can see the utilization's gone up to 100% here. And you can kind of, this is a very basic way of tracking things, but again, it's a first glance of like, am I actually using the GPU? I'm gonna run my script that claims to use the GPU. I'm just gonna do watch NVIDIA SMI and see whether the GPU does something. Does a process get allocated? Does it get some memory allocated? Does it use the GPU? But that's, you'll get that kind of in any environment that you want. There are other commands as well. I think that this tells you that you can use like, if you have lots of GPUs, you can just list them in like a quite concise way. It's more useful if you want to be like, oh, I want to run this script on this GPU and this script on this GPU, and so I need to tell it which NVIDIA. We have this. You can do like NVIDIA visible devices. Oh, there's a bracket in there. Get rid of that. I could do NVIDIA visible devices equals like that one, and then like Python my script or whatever, and that script will only see the GPU that I've exposed it to. So if you're logging into some research machine and it's got 8 GPUs in, and you want to be thoughtful about how you're running things, you can mask them out that way. And NVIDIA SMI will show you the UUIDs and things. Now, one tool that I really like, this isn't an NVIDIA tool, but it's one that's just a community one that is nice. If I just do apt update, there's this tool called NVTop. So if you've used BTOP or HTOP or top or whatever, there is an NVTop. And it shows you more than just NVIDIA stuff. But if I run that, then I do NVTop, I get this kind of graph, this like timeline view of what's going on. So the yellow line here, you can't really see that it's yellow on this screen, but this yellow line is my memory usage. If I just let me allocate a bit more memory, we should see the memory usage go up a little bit, right? And if I do my function to do some compute, we'll see this green line of my utilization jump up to the top. And so we can see utilization over time. This kind of gives you like a slightly better indication into like how your script's behaving. You can kind of keep this open and watch the script running and try and see like how it's using it, right? Like that operation, although it's a silly operation, is very efficient because it fully utilizes the GPU. It jumps to 100%, it uses it continuously. But it appears to be very efficient. I'll show you why it's not in a minute. But this graph will show you like, oh, I'm 100% using the GPU. Whereas you might do other things and you'll see spikes in it, or you'll see like, oh, it jumps to 50% for a little bit and then it drops down and doesn't really do anything, and then it jumps up a bit, and you kind of not fully using the hardware. And so that's the point that you can go in and be like, why is this happening? What other bottlenecks have I got? Is this IO bound? Is this, am I falling back to the CPU when I'm not expecting? All these tools kind of show you these different bits and pieces. So I like NVTop. It kind of gives you that next step beyond watching NVIDIA SMI. Okay, now let's install this. This is the EuroSciPy systems stuff that I was talking about before. So for those of you that wanted to follow along, hopefully you've downloaded that desktop application and installed it. That's just the viewer. It's like the front end of it. But on this remote machine, we also need to install the profiler. And I'm going to do that with apt as well. These are the things that we haven't yet packaged in PyPI and Conda and stuff, right? Like these are other parts of our toolkit that hopefully we will package up and put in kind of normal places at some point. But I'm going to just install this EuroSciPy systems package. And this is installing all sorts of stuff. I think it's basically installing the same thing that we installed locally. But the main thing that I want out of this is this command line tool here called nsys. Come on. So once I've installed all of this, if I do which nsys, I should see that I have an nsys in here. And we can just, we can see which version we've got and things here. And nsys is our like profiler tool, right, that we run to kind of track what's going on. It does require some like Linux kernel configuration stuff. The driver install should deal with that for you. If it doesn't, it should walk you through the docs of that. Everything works nicely in the Brev environments because we've set these up. But let's go through some examples. We'll start with like what we would consider to be normal Python profiling tools, and then we'll move to nsys in a minute. So I'm just going to reactivate my Python environment again. I think I've already got that activated. Let me just check my Python. Yeah, okay, that's the Python I'm expecting. So let's run a little script just to make sure I've got all the packages that came from the environment as well. This should just show me my NumPy version and that kind of stuff, and that I have a GPU. So yes, that's good, we have a GPU. Okay, This isn't the order I was hitting. That's fine. There's a little example script here. Let's actually have a look at this. It's called GPU probe CUDA core. And this is just a little example script to show you how we can use some of these like CUDA Python libraries. Right, so when we installed CUDA Python with the Python package manager, we can do this like import CUDA or CUDA.core. And there's a bunch of stuff in here for kind of accessing the plumbing of the GPU. And you can use this to get a bunch of the same information that is in NVIDIA SMI. You can get it programmatically in Python in case that is of interest to you. So you can write your own tools, your own profilers. You can print stuff out as your code is running if you want to kind of track that. It's actually how we implemented the dashboard, right? It uses these libraries in the Jupyter interface. So we can do things like get the number of devices on the system. We can grab we can iterate over the devices. We can print out its name, what CUDA compute capability it has. This is our kind of API, high-level API version. And then you can print out the memory and stuff. So if I run this little script, not that one. If I run this little script in my command line, it should print out, I've got this L4 NVIDIA GPU. It's got compute capability 8 and 9. I've got 22 gig of RAM being reported, and I'm using some of it. I'm gathering that same information in Python programmatically. So these are kind of, what's the best way to explain?
I didn't hear that question.
Oh, what's CUDA compute capability? I'm trying to think what's the best way to explain that.
Architecture.
Yeah, it's kind of the features, the architectural features in CUDA. So this matters more to you if you are building things with the CUDA language and you want to know what you can use, what features you can use of the hardware. Yeah, you could think of it as like an instruction set, like you would think of like x86 64 as an instruction set or ARM as an instruction set. We basically change our instruction set with every single GPU that we release, and that's like a whole complicated can of worms that I don't really want to talk about. So we try and simplify things by this like compute capability, which is kind of saying like which GPU low-level instructions exist for the CUDA developers. Yeah, and we tend to support two. There's like a rolling window of support. But you'll even find GPUs in the same generation might have different things. And this is partly why these packages are so big as well, because CUDA code is a bit weird in that by default, if you build something, it will compile that code for every single GPU architecture that is kind of current and relevant. So think of it like if I wanted to compile some code on my laptop, and it's going to compile an ARM version and an x86 version and a MIPS version and a whatever version, and it's going to put them all in one binary, and then the operating system will decide where to start executing. Like that's kind of how we package CUDA stuff, and so you end up with a lot of duplication, which is unfortunate. If you're working on a machine where you know exactly what GPU you have and you're never going to change, and you have a whole cluster of them and you're only ever going to use that one, then you can add compiler flags to just compile the instructions for that thing. But we're getting into like exciting off-road stuff that we shouldn't have to care about too much in this group. Okay, so let's look at some more normal profilers. So if you're profiling some stuff in Python, you would probably use something like cprofile and look at it in SnakeViz. So let's do that just so that like have a little look at these tools. So let's download this data set. And we're going to use Xarray. Let's just check that downloaded. We're going to use Xarray to open this data set, right? This is a netcdf file. And we're going to have a look at what's inside it just to make sure it's there. So this is some air temperature data. It's a 3D shape. It's 60 meg. So in terms of like weather and climate data, this isn't huge, but it's a nice little array to play around with. And what we can do is there's a script in here called Xarray CPU baseline. Let's have a quick look in that one. So this is going to open that data set. It's going to start a little timer thing. We're going to make sure that it's in a NumPy array, and we're just going to reshape it, take a mean, and we're going to do an SVD on it, right? This is some operation that is going to use some amount of compute. And we're going to kind of play around with some NumPy type stuff and then print out the results. So if I run this script, this hopefully, if you've used X-ray before, this is like bread and butter X-ray stuff that you would do with some data like this. And this is just normal X-ray, vanilla. I could run this on my laptop, I'm not using any GPUs, and it's just showing some of these outputs. So that took 6 seconds to run through. Now, if you were going to profile that in Python and see what was going on, you could add C profile in there. All right, so we've got this -m flag to run the C profiler and -o to just specify what file we want to output this to. So let's run that. It should take the same 6 seconds or so, but it's stored this profile. And now we can use a tool like SnakeViz or kind of whatever your preferred viewer is to look at that. Now I'm going to run this. This is running on this like remote machine. So that localhost address is the localhost address of the remote machine. So let me just, what I'm going to do, this is why I like to be able to SSH in. I'm just going to do sh-l, was it 8080? Okay, I think you can also, this might say, there's like a brev port forward thing as well. So you can say brev port forward my instance 8080 to like forward that machine's port to your local machine. So if I just log into there, that port forward's active. So I should be able to just open that in the browser. Yeah, so we see SnakeViz here. And you can see like all the different function calls, you know, this is nice. You can drill down into what's going on, but you can see the biggest amount of time here is being spent in this SVD. And if we click on that, we're spending 5.8 seconds in NumPy's .svd function. And that's as deep as I can drill down. Right? I can't click any more than that into this because NumPy is calling down into some compiled code. C profile doesn't have any visibility into this. And so I can't, you know, profile this. So in Python world, you probably go into other tooling here to start inspecting that. Now, if we were to use CuPy instead of NumPy, this plot would look exactly the same, right? Like the times would be a bit shorter because the SVD would be faster, but it would still be an opaque block where we can't see the individual function calls happening inside the SVD. So we don't know what's kind of going on. So this is where the nsys command comes in. And there's a nice little example here, which there's a little diff so you can just see. This is the same script, but it's called X-ray CuPy naive. And we're going to import CuPy. Once we've loaded our data, we're going to make sure it's on the GPU with cp.asArray. But then a bit later in the script, we're accidentally going to move the data back to the CPU. Right now, like this is an intentional silly thing that you would never do in a real script. But if you're using like a whole bunch of libraries, maybe there's some domain-specific libraries that have been implemented. If they have like a stray accidental copy of data back to the CPU, that might be obscured from you, right, as the end user of that library. We've seen this a lot. X-ray used to do this quite a lot. It used to accidentally move data back to the CPU. We went in and fixed a bunch of stuff. It's actually kind of nice because we added CuPy and Pint support at the same time because they were both having the same issues where units kept flying off and data kept moving back to the CPU, and it was the same kind of bug all the way through. So we fixed that in a bunch of places. But just as an example, we have this silly operation where we think we're doing something on the CPU, we're moving the data to the CPU, but we're accidentally undoing that good work before we kind of copy that back. And so I've got this second window open. I'm going to run this naive script, but in the other window, I'm going to run mvtop. All right, so I've got my graph. Well, let's actually just kill my notebook kernel so that I'm not polluting that graph with anything. There we go. Just going to let that clear. Right, if I run my like naive CuPy thing now, we can kind of look at this graph and see, like, oh, there was a little bit of GPU utilization and we filled some memory with stuff, but then like nothing else really happened here, right? I expected this to run on the GPU, but it still took 6 seconds. It actually took longer than the other one because we spent some time copying to the GPU and then we spent some time copying back, and we haven't done any useful work on the GPU yet. And so using these tools, you can kind of get some understanding of like what you expect the code to do and then measuring what the hardware is actually doing. We could profile this as well, but we wouldn't see a huge amount in here. But if we use the EuroSciPy script, we can do the same kind of thing. So we're going to do nsys profile. We're going to trace the CUDA stuff. We're going to track memory usage, and we're going to output to a file and overwrite it and whatever. And let's run this same naive script with this nsys profile. And we should see that should run for a few seconds. And then it's generated this here, right? This file. So if I do an ls, there's this like profile X-ray CuPy naive nsys.rep file. Right? This is my trace, my profile of what's happened. And so I'm just gonna, for simplicity, I'm gonna go into Jupyter, find that file, and download it, which is that one. Yeah, that one. So let's just download that with the Jupyter UI. Again, you could SCP this or however you want to download that. And then I'm going to open that, and because I've got that EnSite Systems tool installed, it should just open in EnSite. And so this is the viewer. This is that front end. Think of this like the SnakeBiz thing. We're taking this profile and having a look at it. Now this gives you like a full timeline of everything that's going on. And we can zoom in to different chunks of this. I don't know if I can make this bigger. Yeah, there we go. That's a bit bigger. And we can see here, like, we have our Python line that's showing different calls and how much time is being spent and different resource usage and things in there. And then we can see this CUDA call. So we can see we spent a bit of time at the beginning in this CUDA malloc. This is us allocating out that memory when we move the data onto the GPU. And we've got this CUDA host to allocate where we're copying the data from the CPU onto the GPU. But then we've got this other operation here that we can see where, is it that one or is it a bit, I can't remember if it's a bit further now. No, it was that one. We can see here we're not really doing anything and we're copying this data back onto the CPU. And so again, this gives you a bit more of a view into what's going on. And you can dig down into all the function calls and exactly what's going on. I'm going to keep going a little bit because we've only got 10 minutes left, but I encourage you to kind of play around with this stuff after you're looking. Okay.
One question: is this kind of thing that you get from Linux systems?
Yeah, you can think of it as the same kind of thing, but this has like kind of telemetry within the GPU hardware itself, so it's measuring stuff at the device level and reporting it back to you. Okay, so there's another little script in here called X-ray CuPy fixed, and this just this uses the CuPy X-ray plugin and doesn't do any silly things, and so it makes sure that our SVD runs on the GPU. So let's run this instead. There's a weird little tail drop on the end. What happened there? Okay, so we should see that process start, and it's doing something, and it did something so fast that we actually can't see anything on that blip. That whole thing ran in 2 seconds instead of 6. The GPU, this was a small example, right? And the GPU SVD was super fast. But we now have another profile, so let's download that one. Which is that one there. Download that. Now we have a look at this one instead. We can see much more going on, right? So we're allocating this memory, but then there's a bunch of library calls that are happening in the GPU. We can kind of drop down and have a look how much runtime overhead there was and what Python's doing. But we can kind of get this view inside of, these are all the different function calls within the kind of CUDA libraries that make up that SVD operations. This is us being able to view inside and see what's going on. And we can make sure that these are all happening on the GPU instead of being on the CPU. Now there's one last thing in this notebook, I think. Yeah, is it this one? Yeah, okay. So this is kind of showing I don't know, like a situation where you may think you're using the GPU well, but until you dig down into these tools, you kind of discover that there's like some problems in there. So we have another script here. This is called pre-process. Because a lot of the time, whenever you're doing some work, you need to pre-process that data in some way. You're not just going to go straight to whatever the operation is. There's going to be some pre-processing script. And I'm sure many of you have written file loaders and pre-processing functions and all this kind of stuff that you end up chaining together to get to the point where you want to get to. So this little pre-processing script has a couple of things in it. And it all looks relatively reasonable. So let's run it. And trace it and have a look at what's going on. Okay, this is running for a second, using the GPU a bit. Again, these operations are so fast, they're not registering too much in this example. But if I now have a look at the little pre-processing one here, download. If we go and have a look, I don't know how to make this less narrow on a big screen like this. Here it is. Okay. If we keep zooming in, right, at this point we can see, oh, my GPU utilization, in that original graph we had, it jumped up a little bit. Right? It was using the GPU. We saw some utilization, but it wasn't very high, and it wasn't there for very long. And when you have a look, you can see, oh, there is some, I don't know if it's super small on the screen, so I'm sorry. But this little blue line is showing you like, oh, there are CUDA calls. Right? CUDA is being used continuously through this entire section. Right? But if I keep zooming in and keep zooming in, we actually see we're doing all these CUDA calls, but they're all tiny, right? We've basically got a for loop, and we're doing lots and lots of tiny little function calls on small chunks of data as we're going through pre-processing. And we're spending a lot of time in this dead space in between, where you're saying, call the function on the GPU, the runtime does some stuff, it gives you like, oh, the function return, I'm going to call the next function on the GPU. It's spending all that time in there. And so we're not actually doing anything very efficient here, even though we're using the GPU for every single operation. Right, whereas it's much more, this is where it comes back to that NumPy analogy of we need to vectorize kind of what's going on within our code. So instead of like looping over and doing things in this way, right, for cells in range, we want to just do this in a vectorized way. So we're going to take out our for loop that calls all these GPU functions, and instead we're going to chain together some vectorized calls, which can all kind of be optimized and run nicely. Now, this notebook doesn't have like an nsys copy paste bit for that last little bit, which is annoying. So let me just put that together myself. But if I run this pre-processing now, but that ran so fast, like the graph didn't even do anything. But I think now if I download the new, I didn't give it a new name either. But if I open this one, we can see the call's much more substantial, and there's a lot less space, and it ran for a lot less time in here. So to recap for the last 5 minutes, I guess, like there's a bunch of different levels you can use to try and answer that question of like, is the thing doing what I expect the thing to do? Right? I'm trying to use these GPU libraries. I'm trying to get some better performance out of it, but I don't trust that it's doing that, or I can't tell, or it's not giving me the performance I'm expecting. Like, how do I start digging through? So I like to work through this stack kind of from top to bottom. You start with EuroSciPy, just make sure it's even registering a process that's using the GPU. Make sure it's allocating some memory. Make sure you can see some utilization in there. You can do that in EuroSciPy. You can write your own little scripts with CUDA core. You can use the MV dashboard, like whatever it is you want, you can get that visibility. Use MV top, see this graph, see that it's actually doing something, get some proof of life that way. And then before trying to optimize any GPU stuff, optimize the CPU stuff first, right? Use cprofile, look at it in SnakeViz. Just do normal Python profiling to make sure that you don't have any like bad for loops or anything that's kind of wasting time at the Python layer. But you'll eventually get to this point where you just see these big blocks of like, oh, I'm calling into NumPy, I'm calling into CuPy, I'm calling into PyTorch, whatever it is, there's just a big chunk in my Python profile and I can't see inside that. And so if you want to go down that next layer and start poking around at what's in there, then you can reach for NSYS, run these traces, generate these profiles, and look at them in that Insight Systems viewer to get like a deeper understanding of what it's doing. You can see whether memory is being copied back and forth, whether there are like loads of tiny little kernel launches, all these kind of systemic things. Funnily enough, when we did this tutorial for SciPy last week, this happened, and then at the sprints, somebody who was also working at NVIDIA was working on something, and they were contributing something to a project, and they were getting really poor performance, and they didn't know why. And one of my colleagues that wrote this tutorial appeared and was like, let's NSYS run it, let's profile it, and came and had a look, and it was exactly the same problem in that last one, where it was making many, many, many tiny kernel calls in the library. And so they did a little bit of refactoring, and all of a sudden they were getting kind of 100x performance over what they were getting before, because they just kind of hadn't written things in the vectorized way. So there are real world applications of this, I promise. And yeah, that's it. We're kind of at time. I hope this has been useful. Does anybody have any more questions or anything you want to ask before we run away?
Profile question, did you look at Scalene? Does it
What's it?
Scalene, which is a profile, a tracing profile of being run for a few years.
They
can look inside the C code also, so they might.
Oh, interesting. I haven't looked at that one. I know we use like PySpy and stuff to look into things as well, but it still has the same.
So this one can profile CPU and memory, and I think they can do something with the GPU also.
Okay, what was that called?
Scalene.
How do you spell that?
Like a scale, and then yeah, Scalene.
This one? Yeah. Okay, cool. No, we should. Oh, it's Ian Oswald. Okay. Yeah.
It's a one-person project. So
right. Okay, I will add this to my notes.
Because it's supposed to also go for 2 years.
Yeah, I saw it, and then it says. Yeah. No, that's cool. Thank you. Okay, any more questions? Thank you for sticking around. I know this has been a long couple of weeks for a lot of people, so please, we'll have good travels home, and thank you for coming.
So thank you, and the ending meeting will be in 10 minutes, in 1:38. Closing session, sorry.
Where any other big room? Nah, you just look at the Python stuff. Yeah, I don't know. So Ben Frederick's that made it works at NVIDIA now. So I don't know how like into CUDA stuff is. I've not talked to him for a while, but yeah.
About working together because you need the NVIDIA GPU. If I have a silicon, but can I just like an or is it now outdated and everyone was working on virtual machines?
You probably can, but I think you'd have a better experience with version of game.
Yeah. But the internet connection was that for.
I mean, it depends. If only Jupyter is coming over the internet connection, right? And, it's Where's the data that you're working with? I guess.
My computer for now.
Okay.
So I can make your.
Yeah, I mean, that would be the thing. I would be tempted to like move the data into like S3 on AWS or something, and then use a VM on AWS to work on the data and try and get it off the machine and into the cloud. I think it that way.
And is there any educational platforms? I would, for example, for students, something.
Yeah, so we have actually for the Deep Learning Institute. But this has all the kind of educational material and stuff. Yeah, there's this kind of stuff, but
Okay.
go and have a look in that.
Is there anything to tell me? Thank you.
Hey, Matt, I'm curious, what's the opinion of NVIDIA with modular? Versus, hacking away in terms of. Like, you don't have to have an answer to that.
No, I mean,
Or do that. Or do that. It's not open source.
I'm not entirely sure what you're talking about. What's
Okay, yeah, it's,
Mojo?
Peter of Motor.
Mojo, yeah.
Yeah. The people behind it, like, they think down to the easy. So you go without being good at no or it's not itself. Because I wonder like what's the biggest stage data like you guys that work about you work on as well.
Yeah.
It goes from that like useful random somebody.
No. I wonder where. I don't know. I don't expect it to be right. But I think like it's at the end of the day we're trying to sell people. And a lot of what I get to work on, I get to open doors and get the right people and help people about all the stuff. And the deal is you can do all the stuff free if you can buy it. And take the time to chip away at that cycle is not.
Yeah, I get it though. So you have an aid. I saw the acquisition when it happened like that. It happened. Now it's the threat. US. Yeah. So I guess this answers the question.
Yeah, I mean, it exists. We put down a bit of our internal platform. Team that built forever. Now, there's a certain amount of frustration. Either you're asking to do it, but they won't give it to you in a well packaged way. And this is true. They want to figure out different issues that they come up with that. Looking for the driver this way, two libraries, two things. The right next to that, so the kind of unique way. But like as you saw, you're paying NVIDIA and NVIDIA is paying effectively, which that doesn't appeal to everyone. Like all the big companies, they already have a place strategy. Where is no one have it? Now I know for a second